If your screen has pixels that are green, red, and blue, then where did the yellow you're seeing right now on your screen come from? How did these three colors manage to create yellow? Why do all screens use red, green, and blue? Why are all screens agreed on these three colors as pixels? Forget screens for a second. Even the cells that receive light in your eyes are actually RGB, red, green, and blue. So where does yellow come from? Everything around you in technology that you use daily and benefit from, know that it's built to trick something biological inside you. All screens are RGB, red, green, blue, because your eyes see the world like that. You can't tell screen manufacturers to add a yellow pixel. That would be a waste of resources, because you don't even have a yellow receptor in your eyes. It's obvious there's some trickery going on here. So, where's this trick coming from? Let's go back to the basics. Your experience as a human being with technology, whether it's screens, cameras, or anything visual, know that all of it is built for your eyes specifically. Let's start with the sensors themselves. How do they give us the color yellow? Okay, we've got sensors, each with a wavelength, peak they can detect. The peak means the maximum wavelength it can respond to. There are three of them. And the wavelength range, each of the three cones, let's call them cones because that's what they're called in English, cones, covers is specific. So, for example, let's say we've got a red pomegranate here with a wavelength of, say, 560 nanometers. That means it's closer to the sensor with a peak of 564 nanometers than the one with a peak of 534. So the sensor most responsive to the pomegranate's light will be the red sensitive one. But there's something important. It's not only the red sensor that reacts to this wavelength. It reacts something like this. The red sensor reacts by about 70%, because 560 nanometers is closer to its 564 nanometer peak. So its reaction is stronger. Your brain receives these signals, processes them, and says, okay, red. All this processing happens in your brain. If your brain decides that these same percentages correspond to blue, it'll make it blue, it doesn't matter. In the end, it depends on how your brain processes these ratios and how sensitive each sensor is to different wavelengths. Okay, good. Now we know that all the sensors in your eyes respond to wavelengths differently, and that's what gives color in your brain. So, what about yellow lemons? Let's apply the same logic. Yellow has its own wavelength, but it actually sits beyond the peaks of all the sensors, usually around 580 nanometers. That's the wavelength of yellow. So, how do the sensors interpret 580 nanometers if it's above all three peaks, red, green, and blue? They respond something like this. Red sensor reacts about 75%, green sensor about 50%. Blue sensor basically doesn't react at all. You might say, wait, that's not 100% total. Yeah, the previous example I just made, them add up to 100% as a simple example. But in reality, it doesn't have to, because the sensors work independently. So the blue sensor could react 100% and the red 100% at the same time. It doesn't matter. Anyway, that's how the sensors react to the wavelength of yellow. Red and green. Last time I checked, mixing them doesn't give yellow. So what's happening? Let's say I go to a color mixing site and mix red and green at equal levels. I get a weird color. I don't know what it is. Orange? Brown? I'm not a painter. Painters? Tell me, what color's that? Anyway, it's not yellow. Close, but not yellow. Even if I increase the red and green levels, it still isn't yellow. So why does this mix appear yellow to us? Okay, think of it this way. Your brain recognizes activation patterns. Like, how much did this sensor activate? How much did that one activate? It doesn't say, oh, this one got red light, this one got blue. That's not how it processes color. It processes patterns of activation. Humans are used to the natural world. You see a lemon, a banana, each has a unique activation pattern for the sensors. So your brain labels that pattern as yellow. So literally, your brain decides that this color is yellow. The cones just detect light photons, their energy and wavelength. And since photon energy and wavelength are basically the same thing, these are activation patterns, not colors. And because you're a living being, created with the ability to interact with the real world, your visual system was made to deal with natural things: bananas, lemons, apples, nature, not screens. So, yellow is just an activation pattern of your sensors, like orange and all the other colors that aren't pure red, green, or blue. All right, stop philosophizing, Raid, and tell us, why can I see yellow on a screen, even though there are no yellow pixels, giving me a yellow wavelength? In real life, yellow objects actually emit a true yellow wavelength, so it's not fake. But how does a screen give us yellow when it only has 3 pixel colors? And mixing them physically can't make real yellow light. Well, scientists looked at how your eyes react to real yellow in the real world, and then used the same RGB pixels to mimic those same activation ratios. So, the lemon on your screen activates your sensors just like a real lemon would: 75% red, 50% green. Now your brain sees the exact same pattern it would see in real life, and it has no other choice but to say, "That's yellow," even though the screen only gave you red and green light, not an actual yellow wavelength. So your screen gives you 2 wavelengths, red and green, instead of one true yellow wavelength, but with the same activation pattern your brain expects. So sorry if from now on you see yellow on screens and realize it's an illusion. Your brain might start buzzing a little. And this idea doesn't just apply to yellow. It applies to most colors that aren't pure red, green, or blue. All of them are tricks of activation patterns that make your brain think it's seeing another color. And notice, I always say, your brain is tricked, not your eyes. Why? Because your brain is the interpreter of the outside world. It's used to dealing with the real, living world: trees, fruits, animals, nature, the sky, the sea. It sees those through patterns of sensor activation. So, if you manipulate those activation patterns correctly, you can trick it. Humans have 2 main types of light sensors: cones and rods. Cones, we just talked about them, detect color. They're divided into 3 types: red sensitive, green sensitive, and blue sensitive. Rods are specialized for darkness. When it's dark, that's when they kick in. That's why sometimes in the dark, you can't see color, you just see shapes. Rods are more sensitive because they need to be in low light. They're always there, but their usefulness increases in the dark. This is part of how humans were made: to live in the real world, not on screens. Here's another interesting fact. What about the brains of other creatures? How do their systems work? Humans have 3 cones. We just talked about that. But some types of shrimp have 16 cones, each sensitive to different wavelengths, with different concentration and even different processing. They can see ultraviolet light, visible light, probably even my conscience. So, the 3 cone system we humans have, it's actually not common in nature. I've already made videos on the channel where I explain things like this, like how wireless things work. Even a full video about screens, the different types, and how to choose the right one if you want to buy a monitor or TV. So, if you're interested in that, you can find it on the channel, or you can subscribe for more content in the future. See you. Peace.